welcome to the second video of Lecture 2. Today we will talk about random experiments and probabilities. In the previous lesson we talked about philosophies of probability and also reviewed some basic concepts from set theory. This lesson introduces the mathematical theory of probability, which is simply a function that assigns numbers from 0 to 1 to a certain event, which is a subset of interest from the sample space. The theory is based on 3 axioms that we will talk about and also discuss some definitions that can be demonstrated from the axioms. In summary, this lesson tries to bridge what we already know from set theory to the real world when we try to solve problems that involve probabilities. So in the real world, we have the concept of random experiment. And what is a random experiment? Well, it's a process by which you observe something that is random. Before you roll a dice, you do not know the result of it. So that's an example of a random experiment. But random experiments have something special about them. You do not know what it will come out, you do not know the outcome of them, but you know what can happen. So you know the range of possibilities of results, of possible outcomes. As we have previously studied, the set of all possible outcomes is the universal set, or in the concept of a random experiment, we call it the sample space. So for instance, consider the random experiment of rolling a dice. The sample space is the face of the dice, being 1, 2, 3, 4, 5, 6. While if you toss a coin, which is another random experiment, you can expect to find heads or tails. If you observe the number of goals that are scored in a soccer match, that's another random experiment. And the sample space is 0 when 0 goals have been scored, 1, 2, 3, 4, and until infinitive. Sometimes we repeat an experiment several times, and in that case we consider that each performance of a random experiment is called a trial. Consider the toss of a coin. You can do it just once, but you can do it twice, or you can do it 3 times. In the case of tossing a coin 3 times, the sample space becomes much larger than when you just toss the coin 1 time. Because the outcomes can be, for instance, heads, 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 or heads, tails, heads, or tails, 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 and so on. In probability theory, we study random events, and the goal is to try to assign probabilities to certain events. And an event is just a subset of the sample space. So that's why it's so important to know concepts from set theory so that we can play around with probabilities. So for instance, consider that in the rolling of a dice you are interested in knowing the probability of the likelihood or the chance of getting an even number. In that case, the set of interest is the set E with 2, 4, and 6. If the result of our random experiment belongs to set A, we say that event A has occurred. So an event, in other words, is just a collection of possible items, a subset of the sample space, as we have said. As you may guess, the probability of event A, in this case, is 50%. But how do we calculate it? Well, that's the goal of probability theory. Probability theory tries to find tools and instruments that enable us to calculate probabilities of events of interest. So what happens when we assign a probability measure to a certain given event? As you already know, a probability is just a value between 0 and 1. It's just a number. And when it's 0, it means that the event is impossible, and when it's 1, it means that it's always certain. It will always happen in the future. So probability expresses how likely an event is. In order for probability theory to estimate the probabilities of events, it uses, or it has its foundations on 3 axioms. The first axiom being that the probability of a given event is always greater or equal to 0. The second axiom being that the probability of the sample space equals 1. And finally, that the probability of the joint events are the sum of the probabilities of each of the events considered. So let's do an exercise. Let's roll a dice and let's try to find the probability of getting 1 or 5. For you this may be very easy to do, but let's try to do this with simply the axioms of probability theory. So you know that the probability of the sample space equals 1 because that's one of the axioms. And in this case, the probability of the sample space is the probability of the union of set 1 with set 2 with set 3 and until set 6, which, because of axiom 3, is the sum of the probabilities of each of the sets. So it's the sum of probability of set 1 with the probability of set 2 and so on. Because you know this is a fair dice, you know that each probability of each set equals the probability of the other set. So the probability of the sample space is 6 multiplied by the probability of set 1. So the probability of set 1 equals 1 over 6. Which is also the probability of set 2 and the probability of set 3 and the probability of set 4, set 5 and set 6. We also know that the probability of E is the union of two events of interest, 1 and 5. So we can apply axiom 3 again. And we get that the final probability equals to the probability of set 1 summed with the probability of set 5. Because we already know the probabilities of set 1 and set 5, we can just sum. And we end up with 2 over 6. If you analyze these probabilities, you recognize that this is just the cardinality of the event E over the cardinality of the sample space, the number of elements in the set A over the number of elements in the sample space. So this is the way that we typically calculate the probability of a given event. So it's the cardinality of the set of the event over the cardinality of the sample space. So, or in other words, the number of favorable cases over the total number of cases, the total number of outcomes. And this is basically the most general foundation of probability theory. So you have also other interesting definitions that are worth knowing because they can be of use to solve some problems from probability theory. So these are the learning objectives for today. Today we interconnected concepts from set theory with probability theory, and we have seen why it's so important to know set theory to actually handle probabilities, because probabilities talk the language of sets. Probabilities are always calculated for sets. And perhaps the most important thing that we have talked about is how to calculate the probability of a certain event, being the cardinality of the event over the cardinality of the sample space. Also, it's important to know the 3 axioms of probability. These are assumptions that we have by which all the theorems of probability are based on them. So if you know them, you can actually demonstrate all the other definitions. So with this being said, you are ready to do some exercises on probability theory, and you have reviewed some of the most important concepts of probability so far. In the next lesson, we will talk about conditional probability. So until then, thank you for watching and see you next lesson.